Hi everyone and welcome back. This is CCCAMP CTF 2023 hosted by ALLES. It was a pretty fun CTF, a little bit difficult. I was only able to solve 5 of the challenges. I spent a lot of time on Pwn Curly and was not able to get it, so I am very excited to see the write-up for that challenge. But with that, let's jump in. This is misc --x. It says, did you know that you can mark executables as non-readable? Check out user bin flagcheck for an example. We're given flagcheck.c and an SSH connection string. So for this challenge, this is the C file. There's nothing really special about this. They kind of make it look like you can brute force the flag character by character, but because of the bounds check, I don't think you can actually do that. But yeah, pretty much very simple binary. You give it an argument and it tells you if the flag is correct or not. So what's weird about this is they give us SSH access to this box, and we can see this binary, user bin flag check. So we can see that this binary exists, and in this binary there is the flag, and we're allowed to execute the binary, but we're not allowed to read the binary. So like if we were able to run strings, this would be obviously a trivial challenge, but we're not allowed to read it. But we, like I said, we are allowed to execute it, which is fun. So execute, but no read. And so the challenge was like, how do you figure out a way around that? There's probably multiple solutions. My solution was to use ptrace. So ptrace is just an API or syscall that you can use for tracing another process. This is how debuggers work under the hood. And this is my solution code. So basically I just wrote a little C program using the ptrace API so that I can inspect that process and see what the flag is. I had a little bit of trouble getting some of the ptrace APIs to work. Specifically, peak data and peak text weren't working. Ideally, I was just going to like scan memory and see if I can just find the flag, but that wasn't working for some reason. So I did something a little bit hacky. I ran the program in GDB locally to see how it works, and I noticed that when it does the comparison, this comparison right here, it's going to load the flag into the register RDX. And so basically, what my code does is I check to see if I'm in like this function or around, in the main elf section. If I'm in the main elf section just by checking RIP, I wait until RDX changes and RDX is holding a value that could be a character, and then I just print it out. Not very scientific, but it works, like I said. So this is what the ptrace API looks like. So we're setting some buffering. We're going to fork. So basically, we're just going to fork. So there's going to be a child process and a parent process. If we are in the child process is going to tell the ptrace API that, hey, like you're allowed to trace me, which we specify here. And then the child process is going to execute the flag check binary, name flag check, and then this is the argument. And we're just setting a bunch of A's. We don't really care about it. We just need it to be as long as the flag. The parent process then, so the parent process is allowed to inspect the child process. And from here, we're going to create a reg structure. So this is a value that'll hold the CPU registers in a second. RIP, previous, not too exciting. And so this is the ptrace single step. So if you use a debugger, again, you've probably done this before. Now we're able to single step the process. And so what I'm going to do in this while infinite loop, I'm just going to single step the child process over and over and over. And I'm going to then do a ptrace get regs and see what the register values are after each little step. If the registers, the RIP, so the instruction pointer is less than libc, I know that the main elf section is probably like OX64000 or something like that, or 56000 or something like that. Basically, it's going to be less than OX7FFF or 7F000. So if we're in the main like binary section, I check the registers. If RDX looks like it's holding a character and it's not equal to the previous character value, that I print it out. And that's pretty much it. A little bit hacky, but it works. There's one little issue because I'm making sure it's not the previous one, and it's possible the previous one, like ALL, it won't print the second L, but it's easy to figure those out. So to load it onto the remote host, first I convert it to base64. So I just dump it into CyberChef, base64. I copied it. So now I'm here. I'm going to do echo. I'm going to print all this stuff out, and I'm going to call it ptrace.b64. Then I'm going to cat out ptrace64, then I'm do base 64 decode ptrace.c. So just moving it. So now we should have the file over there. You can try to copy it out with like double quotes and stuff or triple quotes, but I don't know. I prefer to do this. So now we have the code. Now we can do gcc ptrace.c. And we don't care about that. Cool. And it should be working. So now we'll just do a.out and we'll see what we get. there we go. It printed out the flag. So really fast. Like I said, it's just going to go through, see if RDX is a character, and if it's a character, it's going to print it out. And thankfully, RDX isn't used for anything else, so nice and simple. From there, like I said, it's going to check if the previous register isn't equal to the current register. So anytime there's 2 characters in a row, it's not going to work. So is it is it 2 C's? Oh god, this is embarrassing. I think it's this. And actually, there we go. So surprisingly similar to set UID processes, but not actually secure. This is Web Cybercrime-Society-Club-Germany. It says you are Agent Jason Bourne. Haha. Your mission: hack this new cybercrime website before it is too late. We're given a zip file and a URL. This challenge is fun. Basically, in this, we're going to be stringing together a bunch of tiny little bugs, and from there, we're going to have a full exploit chain, and we'll be able to get the flag. This is the website. You know, it's kind of silly, just some art. You can log in, sign up. Once you're logged in, there really isn't that much you can do. It's more of like an attack and API sort of challenge. So this is the API. The API, it's all written in Python. I'm just taking a step back. It's all Python. There's some user DB stuff that's being stored as JSON. There's a flag.txt that exists on disk. So our goal is to leak this flag.txt file. That's pretty much it. Like I said, there's this API, and we can hit it and perform these actions. We can delete accounts, create accounts, edit accounts, log in, log out, error, and admin. We can do everything except for the admin route because we're starting out, we're not an admin. But it seems like admin is probably our goal. And if we look at this API admin, we can see that when we are admin, we can run the date command. So like the Linux date command, and it's going to do a subprocess.run. We can do more than that, which we'll talk about soon. We can bypass this validate command thing, but this seems like our goal. So our goal is to become admin. Like I said, there's a lot of little bugs in this. So I feel like I'm just going to go through the code. It's going to be all over the place. But I'm going to talk about all the little bugs all over the place, and then we'll string them together. First bug here, this check activation code. This is used when you create a new account. It's weird. It does a sleep 20, so we're not able to brute force this. And what it's going to do is it's going to generate a random 4-digit number and check that our activation code, when we generate a code, matches that. So this is our first little hurdle to bypass. Thankfully, this one's a little bit easy to bypass. Activation code doesn't have a length restriction, so we're just going to pass a super large activation code that just has every number from 0 to 10,000. So all 10,000 of them. And so that bypasses this. We still have to wait 20 seconds every time we register an account, but it is what it is. This delete accounts function is interesting. The delete accounts API makes it look like you're only going to be deleting your own account, but we're actually able to specify multiple emails in here. And so what we're going to do is we're actually going to delete multiple accounts, our own account and also the admin account, which, you know, is part of the solution. This is boring. This is that validate command thing that the admin runs. So it said that the admin command, or the admin, is only allowed to run the date command. And so we're going to pass a string that's going to validate it. But this doesn't necessarily have to be a string. This could be an array. We're passing JSON back and forth, and it doesn't check to make sure it is a string. So we could do length of array is equal to 4 and array index of date equals 0, and that's very true. And then using that, you know, we can do special stuff here, which I guess I'll talk about now. So if we can specify an array like this, we can pass extra arguments to the date command. And specifically what we're going to do is we're going to use a GTFO bin. So you can go to this website, GTFO bin, and it basically just outlines different ways that you can abuse program arguments, I guess. And so we would search for date. Date is here, and it says we can do a file read on date if we pass the -f and then a file to read. So cool. So we can read a file off disk abusing this date program, which is what we want. Let's delete this. We need to create an account. To create an account, there's a couple different checks and things we need to do. It cannot be the admin account. Eventually, we need to be the admin. This is the admin URL or email. We'll come back to that later. We get to specify a group ID and a user ID. This is another check we need to bypass later. I'll just talk about it now. We need to be an admin, we need a user ID that is 9 digits long. But if we look here, it's going to do user ID is equal to 1 plus group ID and user ID, and together length 3 and length 4, the max length is 8, and we need one that is 9. Thankfully, to bypass this one, what we're going to do, instead of specifying a user ID like 121, something like this, we're going to specify 1E10. And it's doing this strange JSON loads, but JSON load allows the scientific notation. And so this is just going to be a huge number. So when this comes together, it's going to be 1E10, and this number, whatever group ID is, we can specify whatever we want. This is going to be, a billion something. Group ID, user ID. This is that activation code thing we talked about earlier. We're just going to specify every number between 0 and 10,000, so we bypass that. And then after that, it'll add our user, and we're good. So this delete account function is interesting. So it's delete account, not delete accounts. And it seems like, you should only be able to delete one account. But they do this kind of weird thing. It's delete accounts, and it passes every value in the data object that we supply. So backing up, it's going to check and make sure that the email field in the data object matches our email, but it doesn't check any of the other key values. And so we're just going to specify, I think I did email 2, which isn't validated, and email 2 will be the admin user. So we're able to delete the admin user's account. There's this edit account feature. Again, this is just a lot of little bugs that we're all going to string together. We can, in the edit account, we can change the user email. What's interesting about this one, the changing user email, it makes sure that the emails aren't in use, but it doesn't check that the email is not the admin email. So we're not allowed to register a new account with the admin email, but we can swap an existing account to the admin email, assuming that the admin email doesn't exist. But like I said, we're going to delete the admin email and then do a little swap so that we can become admin. Then we can log in, nothing too exciting, log out. And here's that API admin call again. Like I said, we're going to do the date, and then we're doing the GTFO bin so that we can read files off disk. And that's pretty much it. That is everything that we need to exploit it. And the rest is just like serving templates and nothing too exciting. Cool. So this is the solve script. Like I said, we're doing a lot of little things. Pretty much just going to go through. So here's the base URL. This is the admin email. I defined 2 functions, so little helper functions. One is to register a user, one is to log in a user. Nothing too exciting. Like I said, the first little bypasses that activation code. I'm just generating every number from 0 to 10,000 right here, so that when we activate an account, it'll be, it'll have that activation code. I also, like I said, that group ID, I'm specifying an E10, and so that way, it's just a very large number, and we bypass that check for admin. I guess I didn't show the admin check. User to be is admin. It's right here. We can see to be an admin, you have to have this email, and your user ID has to be over this number. That's all. Cool. So first thing we're going to do is we're going to register an account. Then I'm going to grab the cookies and I'm going to log in as that user. Then I'm going to delete the admin user. And like I said, to do that, I'm specifying in the data fields. I'm specifying my email, so I'm going to delete this account. But they don't do validation on any other key value there, so I'm just specifying email 2 and the admin email. And so because of the way the code is constructed, it will also delete this account. So cool, now the admin no longer exists. Then I'm going to re-register Sloppy Joe Pirates because I just deleted that email, re-grab the cookies, and now I'm going to edit my account so that my email is the admin's email. Cool, so now I am in admin. Then I just print it out just to verify that everything's working correctly. And then the last thing we do is we use that GTFO bin and the date API to leak the flag. So we find out that the flag is user source at flag.txt, and we just leak it using the date command. You have to pass one other thing because it needs to be length 4. So I just found I did man date, and I found another flag, which is the debug. We don't really care. And that way it's length 4. And from there, we should get the flag. So let's run it real quick. Python 3, solve.py. Registering a user. I probably should have started this. It takes 20 seconds. I'll probably speed up the video. Sweet, it worked. We can see we have the flag down here. Yeah, the date wasn't able to parse it, but it still leaks the contents. So you have Jason Bourne strikes again. So lots of little bugs, but overall pretty fun. This is web awesome-notepad. There's some flavor text. I don't think it helps too much with the challenge. Then there's a notepad.zip and a URL. So if we go here, there's 2 different things. You can supply a note, and they give some example notes. We can create notes, and yeah, we don't actually use these notes. They're not important to the challenge. Then there's also this report a bug, and we can report a bug here. And there's a background script where some Firefox browser will view those bugs. And that is the front end of the challenge. This is the code for the challenge, or I guess that's the solve script. But this is the code for the rest of the challenge. I think the hardest part of this challenge was just going through all 5 containers and figuring out what you're supposed to be doing and what you're supposed to be exploiting. Once you know what to do, the challenge is very simple. It's a lot of just wrapping your head around this challenge. So there's 5 different containers. We have the Notepad API. So this is like a GraphQL little server, and it has the database, and this is how we make our API calls. We have a React server here, a Notepad, and this is just the React code that we just saw. We have an Nginx server just caching, or just serving content. I don't even think it's caching. Then we have this browser. So this is the Firefox browser that is going to be like, you know, our headless admin bot. And every 30 seconds, it's going to go to the ticket app root and just view it and then close and sleep for 30 seconds, I guess. So every 30 seconds, it's going to look at all tickets. Like I said, there's two different things. There's notes and there's tickets. As part of the solution, we don't care about notes at all. We only care about tickets, which are the report an admin bug sort of thing. It's going to request from ticket app root, and this is the note admin. So there's this other web server over here. So this is like some background admin portal that I don't think we can access by default. And we can see that the flag is defined here. So on this web server, it's going to set a cookie with flag is equal to ALLES and redacted. Cool. And it only has one, I guess, page if you do a GET request to it, and it's going to query, using this GraphQL syntax, the Notepad API for all tickets and embed them here into this page. We can see it's manually constructing HTML, so this is probably very dangerous. And so this is where the issue is. So ticket issue, and we can see we probably have an XSS here. So if we go back to that Firefox script, this Firefox script every 30 seconds is going to connect to this note admin portal, this thing, and just render the HTML. It looks like we have an XSS here, and it's also going to set the cookie of the flag, and we don't see any cookie protections like HTTP only. So pretty much we just need to figure out how to XSS this. And we see the XSS, so somehow we need to embed an XSS payload in a ticket issue. Cool. So if we go back to this is Notepad API. Let's take a look at it. We want, I think, resolvers. So we normally the front end code is using this add ticket thing. So we specify a ticket, args issue, sorry, just the issue. It's going to construct a random ID. It's calling this rep function before it saves the issue into the database, I guess. And this rep thing is going to do replace, and this is our XSS filter. So it doesn't look like we can insert a ticket using this add ticket call that would have an XSS. But if we scroll down just a little bit, there's this other call called save ticket. The front end code doesn't use this one. This is just some GraphQL query that exists. We can see that we get to specify a ID and an issue, and it's not doing that filtering on this issue thing. And so, yeah, that's pretty much it. This is just a GraphQL mutation. We're allowed to call this. And so that was the challenge. Basically, we're just going to call this GraphQL endpoint, save ticket, put our XSS in this issue. Then every 30 seconds, that Firefox script is going to download some HTML from that admin portal and run it. If the XSS is in there, we're able to exfiltrate the cookies, and that's it. So like I said, it probably took a good like 30 minutes, an hour, just like trying to understand what all this is doing. But once you see it, like the bug really isn't too bad. And the exploit is just a single request. So this is the base URL. Let me make sure it's correct. 504. Yep. We're going to do a post request to the GraphQL endpoint. To find these, you can see I have that thing copied above. I just type in some text here and hit send. Then we go to the network tab, and you can see what a GraphQL request looks like. We're doing an insert operation, a mutation, and so we can see that this is what it looks like. Basically, I just took this, I copied it over, and I put it right here. So this is what add ticket looks like, and we want to use save ticket. So I copied it, request.post, let me make this a little bit bigger, GraphQL. So this is what we're going to send it, operation name. So instead of add ticket, we're doing save ticket. These are our variables. I call it the ticket ID XSS. This is my XSS payload. Image source is equal to X. On error window.location is equal to webhook.site. We should probably load a webhook. And then encode the cookies. So very simple XSS payload. I don't need the script, I don't think. Actually, I'll just leave it. I don't want to change anything. But it's not a script, it's a image. And then we need the rest of the mutation query syntax. Basically, we're just changing that add ticket syntax to save ticket. It's a little bit different. The old one didn't have an ID, so you just need to add an ID here, rename this to save ticket, add another ID here, and then add ID here. And that was pretty much it. We do all that, we make the post, and it should just work. So let's do Python 3, solve.py. See if the ticket gets inserted. Looks like it was inserted. Then we're going to come back to the webhook site and see. We have to wait 30 seconds, but hopefully it pops up soon. You can already see it. This was the one from previously. You can see I solved it 3 hours ago. Cool. We got a new request, and it's the same flag. Secret mutations are a feature, not a bug. So Not too bad. This is crypto CBC. It says, I came up with this great idea for securely running scripts on my testing server by using cryptography. And we're given a netcat port and I think there were some download files. You can download the download file from the challenge itself. If we look at the download file, we can see we have a little REPL, there's some redacted key, and we get 4 options. We can run a script, we can get the source code of this program, which is how I got this. We can get a script sample, and we can exit. So pretty interesting. If we go to the run script option, what it's going to do is it's going to decrypt the ciphertext we give it, and then it's going to pass it into a Python exec. So somehow it is somewhat possible to execute remote code if we have the proper ciphertext. We're also able to ask it for a sample of code. And so what it's going to do is it's going to take this code sample here, this exit, test talk and key and security is going to encrypt it and give us that ciphertext. Since we don't know the key, this is the only code we can currently run because we can't decrypt anything else correctly. And it's weird that this code just calls exit right at the start. And so this code at first glance looks useless. But if the code was working correctly, it's a very strange code. There's some comments. It's going to check if these values are equal. And if they're equal, it's going to say result is equal to C plus the key minus the last 4 bytes. But then it clears out result. So a little bit strange. Going back to the run script after it executes, it prints out this results variable. So whatever our script does and assigns to results, it'll print it out later. So pretty interesting. And then there's some decrypt function. The challenge was called CBC. We have some CBC encryption, so we know we're going to be doing some sort of CBC attack. It's really not too bad. We're just going to be doing some bit flipping within CBC to get this sample of code to do something interesting. So first thing to start with, CBC works in blocks of 16 bytes, or I guess AES. So first thing we want to do is we want to take and we have one plain text and one ciphertext, and we're going to split those into 16 byte chunks and see what's going on. So this is the 16 byte chunks of the code that we're given. And so I'm going to uncomment it. And so this is what we have. So we have, it starts out with an exit and then a comment AAA, and then some AA, new line, and then another comment, blah, blah, blah. And the trick is to kind of massage this so that it does what we want without doing the things that we don't want it to do. And the tricks we're going to employ is we're actually going to delete the first block, which we can kind of do. It'll have some effects of what I'll talk about in a second. And we can also delete the last couple of blocks. So we're not going to set this reset equals nope. That one's easy. We can just not include that ciphertext. Again, everything is 16 byte aligned. And so what we're left with is AA, blah, 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 and then some more A's, and then a new line. And then A is equal to this. And if A is not equal to zeros, which it normally is, it'll set the result to key. So at this point, again, we still have the ciphertext that we're going to send to the server. What we're going to start doing is we're going to take the ciphertext for these blocks 1 through 11. And what we're going to do is we're going to bit flip right here. And what's going to happen is when we bit flip here, this first block, it's going to completely destroy this block right here. So this is going to turn into, some absolute ciphertext garbage. But as a side effect on how CBC decryption works, it's also going to bit flip this block right here. And so this is going to become a 1. And so what's going to happen is now we're setting A equal to this string. And so now this condition will be false, true. A will not be equal to all zeros because we have that bit flip. And so result will be the key value. The only trouble is this is going to get absolutely clobbered as it gets converted from some garbage ciphertext into plain text, but that's not a problem. We can actually just fuzz it, and eventually we should just get a comment character, by random chance to be at the start, and then we don't really care what garbage is in here because it's going to be commented out by Python. So, and that was pretty much it, and that'll give us the key except for the last 4 bytes, and yeah, that's pretty much it. We're just going to fuzz these last couple of bits. So to do that, this is the key leaking script. I take the plain text. This is the ciphertext. So like I said, we're going to chop off the last block, the very first block, this exit code because we don't want it, and like some of this. And then we're going to cut off the last 2 blocks, which is just this, or it might even be like all the way to here. We're going to make sure it's still length 16. I didn't do anything wrong with the cutting. Then we're going to connect to remote. We're going to take the ciphertext, we're going to cast it into a byte array just so we can manipulate it. And like I said, we're going to start bit flipping near the end because we need the first ciphertext to decode to something that starts with a comment, but it also, like I said, it's also going to bit flip so that one of these bits gets changed so that these strings are not equal. Yeah, and so I just looped over it. I think it ends up being like 180 or something like that. At 180, it's going to be valid plaintext that executes as Python, and we should get the key as the result. So let's try running it. Python 3, key leak. We're connecting, we're sending text, and it worked. So this is the decrypted text that we get after it's doing that decryption. We can see the first line is complete garbage, but we found we were able to brute force one that started with a comment character. So Python just ignores all of this, and we can see this is the bit we flipped right here. So R is equal to this weird string, and that does not match that. And because of that, we'll get C question mark and then sum of the key. And we can see this is the response here. So C and then part of the key. So from this point, we need to brute force the rest of the key. Really not too bad. So I just have another function called keySolve. Very similar. We have the plaintext, we have the ciphertext. I just grab out the first 16 bytes of the plaintext and ciphertext. Where did I do that? Somewhere over here. Yeah, I grabbed the first 16 bytes and the first 16 bytes of both. And then I guess what the key is. The key looks like it's hex, so I'm just going to construct some hex. So I go from every number from 0 to 2 bytes worth of numbers, construct some hex looking stuff, encode the key because it needs to be bytes, and then I do an AES encrypt, and I see if the ciphertext matches the ciphertext, and if we do, then we know we have the correct key. So you just run this code, and eventually you'll get the correct key. Python 3, it was keySolve. Cool, found the key. And so this is the encryption key being used. Now that we have the encryption key, we can send arbitrary code over there because we can just encrypt the plaintext and do whatever we want. So I call this shell.py. So we take our key, we're going to connect to the remote, set up a little cipher. This is the code we're going to encrypt. So import process, result is equal to subprocess, check output, cat flag, and then we encrypt it and we send it over. And that's it. So Python 3, shell.py, we encrypt, send over, and the script runs, and this was the output. ALLES, I'm never using SeeBeeSee again. Fun. The last challenge is crypto RNGEEE. It says, just guess the flag. I guessed it correctly after just 1 min. Easy. Use message 32 to test your guess skills before attempting message 56. Cool. I'm not going to cover all the code for this challenge, but basically this was a Z3 challenge. And yeah, basically it's going to do some key generation, and it's going to give us some output. The output is XORed with the flag. And so kind of doing that, you need to reverse the seed. And once you've reversed the seed, you're able to get back the original flag. And so this is the original code. They do some stuff like rotate left, rotate right, a couple rounds of that. And then from there, the previous seed generates the next state. To solve it, it took maybe like an hour of running the script. So definitely took a while, but this is what the Z3 script looks like. I'll just kind of go over it quickly. So new solver, create a seed with bits. So this is 56 bits seed. Then we create a flag. I don't use that many characters, range 17. The flag is much longer than that. I could make it longer, but it doesn't really matter. The only input we know is that the flag starts with ALLES, exclamation point, and then open bracket, which is interesting. And the rest of the flag obviously is going to be printable characters. From here, one thing we can do to maybe speed it up or be less confusing is the original script used rotate left and rotate right. This kind of weird code. You have to be careful when using Z3. There's like logical shifts and arithmetic shifts, and Z3 uses a different one than Python uses. But thankfully, rotate right and rotate left are functions that Z3 just implements, and so you can get rid of those functions and just use the rotate left and rotate rights. So we got rid of those two functions. From there, the same code, generate random, generate random. This is the output that was given in some file. And so basically we're going to just take a couple of them. I only grabbed the first 15 values. It gets slow after that because these states get pretty big. As part of this, I'm using a new function in Z3 I've never used, extract. And so originally rand_gen is a bit vec of 56 bits. You can extract just the lower 8 bits using this extract call. So this is just a single character. We have a single character, or 8 bits here, 8 bits here. Another 8 bits as the output value, and then the output of our random stream, and the flag is the output that we have. And that's pretty much it. So we do that. We check if the model's okay. I have this print flag function. Basically, I just took it. This is kind of the original code, just massaged a little bit to just see what the flag looks like for each of the seeds. Part of the problem is we're going to generate a bunch of seeds, but not all the seeds are correct. And so we're going to ask for a model. As part of Z3, we're going to print out the C, and then we're going to print out what flag is generated from that seed. But like I said, most of them are not correct. I added this check to see if all the flag characters generated by this seed are in string printable, then printed out the flag and exit. Otherwise, we just add to the model that that seed was not the correct seed, and we generate a new seed. Like I said, I ran the script, or let the script run for like an hour in the background, and we can see it just generates a bunch of seeds that just don't make sense. But eventually it generates the correct one, and it is allies bool lector go bur yeet, and then this very long message. So fun. And that's it. So thanks again, ALLES, for hosting, and I will see you at the next CTF. Cheers.